So thank you very much for the nice introduction. The title of my talk today is Can Formal Language Help RL Agents Learn and Think? So I wanted to start by acknowledging my graduate student, my recently former graduate student, Rodrigo Toro Accardo. A lot of the work that I'm talking about today was part of his PhD thesis in conjunction with his collaborators, Torin Claassen, Rick Valenzano, and some work with Alberto Camacho, as well as other people in my lab. So I'm going to start with language. Humans have evolved language over thousands of years to provide some sort of a useful abstraction for understanding and interacting with each other and with the physical world. The claim advanced by some is that language influences what we think, what we perceive, how we focus our attention, and what we remember. We use language to capture our understanding of the world around us, to communicate high-level goals and intentions and objectives, and to support coordination with others. We use language to program computers, and we use the language of mathematics to understand and model complex things in the world and to think about them. Importantly, language can provide us with a useful and purposeful abstraction that can help us to generalize and transfer knowledge to new situations. So can exploiting the alphabet and structure of language help AI agents learn and think? So the way that I frame this, the way that I want to frame this problem for the purposes of this talk is to just sort of ground it in thinking about an AI, a robot that you might want to, that comes into your home and that has some capabilities and that you might want to advise, instruct, or task in some way, impart some sort of knowledge as you would a human being that might come into your home. So that can be sort of your working model and thinking about what I'm going to discuss today. So how do they use that knowledge to learn? So I'm framing this today in the context of reinforcement learning, and I think that needs no introduction to this crew, so I'll just carry on. How do we advise, instruct, task, and impart knowledge to our RL agents? And more generally, how does an AGI self-incentivize, learn, and evolve? So the opinion, we were asked to express an opinion. My opinion is that the alphabet, compositional syntax, and semantics of formal language can help RL agents learn what to remember and reason. And I'm hoping that I'm going to convince you of that. So the dirty little secret for those of us who, of course, build RL systems is that unlike you and me, if I eat ice cream, I get a plus 100. If I stub my toe, I get a minus 10, that our RL agents fundamentally get no reward that is not programmed by us. We have to program a function. It's a mapping from states to some sort of a scalar value or some sort of function that endows that agent with pleasure and pain, regardless of whether the RL agent is operating in a simulated environment or in the real world. They do not receive that signal unless somebody has programmed it for them. And that function of mapping from state to the reals, or state action, state triple to the reals, is a very sort of impoverished way of writing a reward function. So two real challenges to developing RL in practice are reward specification. It's really hard to define reward functions for complex tasks. And of course, we often get our poor graduate students to do that. And it's also the case that RL agents might require billions of interactions with the environment to learn good policies, just walking around in the dark, searching for signals. So just to give you some examples of the types of rewards that I might have if I had a robot in my home, I might want to say, run the dishwasher when it's full or when dishes are needed for the next meal. Make sure the bath temperature is between 38 and 43 Celsius immediately before letting someone enter the bathtub. Do not vacuum while someone in the house is sleeping. And finally, when assisting someone from a car to the sidewalk, please always open the car door closest to the person, help the person to standing, move them beyond the car door, close the door, and walk them to the sidewalk. What I want to show with these simple examples is number one, many of these even though the reward function is a mapping from state to action, many of these goals or preferences or reward-worthy behavior are temporally extended and quite conditional and quite complex, and of course sometimes contradictory to each other. And then the other thing I wanted to show was with this example of helping somebody to the sidewalk, that you really have to finish the whole job in order to get the reward. If the agent opens the door, lets somebody out in traffic, and then just leaves them there, and that's half of the task. They shouldn't get half of the reward. In fact, they should get a very big negative reward for endangering the person. Rather, they need to complete the task in order to get reward. So many of our reward-worthy behaviors are temporally extended and quite complex. So how do we communicate these to our RL agent? And my answer is language, or in particular, for the purposes of this talk, formal language. So linear temporal logic, for those of you who are computer scientists, you may know about linear temporal logic, otherwise perhaps you don't. It's a beautiful and very simple propositional modal logic with temporal modalities that allow us to talk about properties of traces, properties of the states, evolutions of the state of the world. And it has typical logical connectives like and, or, and not, and implication, but it also has these temporal modalities so that I can say things like next, or until, or eventually, or always, eventually be home tonight, always lock the door before you leave the house, and so on. So this logic is interpreted on both finite and infinite traces. And one important property that it has, which I'll return to later, is it can be transformed into a corresponding automata that corresponds to the traces that satisfy these linear temporal logic formulae. So just a very simple example, do not vacuum while someone is sleeping might be written as always. It's not the case that vacuum and sleeping are co-occurring in a state. And of course, with our syntax, we would write that as a box. So we've done a lot of work using linear temporal logic which is a formal language. It's also used for verification, all sorts of other tasks. We've done quite a bit of work in this area with reinforcement learning, with advice and instructions. And I'm not going to talk about that today, but if you're interested, you can read some of these papers. What I want to talk about is the more general notion of language, and in particular, draw your attention to Chomsky's hierarchy. There's Noam Chomsky on the right, who of course is well known, probably more so for his political views. But of course, early on, he made a very significant contribution to language in terms of defining Chomsky's hierarchy, which was a hierarchy of more and more expressive languages. And what we're interested in the context of this talk right now is the family of regular languages, which we can represent as automata. And certainly some impoverished natural languages people used to debate whether they were context sensitive or context free languages, but certainly a restricted language could be captured in this form. So how do we communicate this to our reinforcement learning agents? What I want to argue here is formal languages and their correspondence to automata. So what I'm going to do in the rest of the talk is give you a very quick flyby of this notion of reward machines. I'm going to tell you what they are. I'm going to tell you how to exploit reward machine structure in learning, show you a few experiments, and talk to you about creating reward machines. And I'm going to do that by just starting with a very simple example. So the example that you see on the left, is an office grid world. And in this grid world, we have 2 coffee stations, very important, a mail room, an office, some furniture, which is the stars. And we have these 4 locations, A, B, C, D. And our agent, this little purple guy, is tasked with doing this patrolling routine of going from A, B to C to D. And once it makes one loop, it gets a little bit of reward, but it has to do it in that order. So we can, I could program this, or my graduate student could program this pretty simple Python code reward to only give the reward function that only give the agent reward once it's reached D. And of course, it needs this counter to sort of remember where it's been before. And that's the way it embellishes the state in order to do that. So what I'm going to argue here is that instead of writing that code in Python or your favorite programming language, I want to represent it as a reward machine, which is basically a finite state, an automata-like structure that uses a vocabulary, a human interpretable vocabulary, because a human is going to be writing this. It need not be in the more general sense, but here for the purposes of a human specifying it, it would be a human interpretable vocabulary. And I'll tell you a little bit more about what these reward machines do. Basically, a reward machine is an automata. So it's a structure like a grammar that can accept and generate a set of strings that adhere to the constraints that I've written. So think back to those nice instructions or wishes, goals, and preferences. Those goals and preferences can all be translated into this finite state automata representation, and any trace that satisfies all of them will be a trace of this reward machine. Here, this is a reward machine for my patrolling structure instead, but that's the idea of an automata, that it's a recognizer and a generator of language. But our reward machine is a little bit more than that, because it's going to generate reward as well. So it has a finite set of states, U0, U1, U2, U3 for the purposes of our patrolling task, an initial state, U0, and a set of labeled transitions where each label contains a guard, which is some logical formula that allows it to transition to the next state, some condition in the world that's been observed, and some sort of a reward function. So here, what we see is that we start with no opinion about where we are, and once we've hit A, we get 0 and we transition. Once we've hit B, we get 0 in transition. Once we get C, we get 0 in transition. And finally, when we hit D, we get a reward of 1. So we get a reward for completing that cycle. So here's a reward machine in action. Again, as it moves within that structure, that function, the agent signals its action, and and a reward is returned. And of course, it transitions as a consequence. And I won't go through the whole detail. So there are all sorts of different reward machines that we can describe. Deliver coffee to the office while avoiding furniture would be this path at the top, and which garners a reward of 1 if we have not hit that star furniture and we get to our sync state, U3. However, if we hit furniture, then we go down into this U2 state and can never leave it again because we violated the instruction or the task. Another example where we don't care about the order in which we do things, deliver coffee and mail to the office. And it may very well be that in some cases, it's better for you to do coffee before the mail because of their relative location. And in other cases, it may be smarter for you to do the mail and then the coffee and then go to the office. And those can be captured in a reward machine. So how do we exploit reward structure in learning? We had a very simple idea. And the simple idea was the following. As I alluded to before, someone always has to program the reward function, even when the environment is the real world. And yet, in reinforcement learning, that reward function is always treated as a black box as far as the learning system is concerned. You know, the agent performs an action in the world, and then the environment gives it a state and an observation. And so the simple idea here is, why not actually give the agent the reward function, allow it to understand what its reward structure is, and allow it to actually manipulate and exploit that structure in learning. And that's exactly what we do. So the agent can exploit the reward structure in the reward function. Here, we're doing it with a reward machine, but I think but I'll argue afterwards, and we've done it with linear temporal logic as well. But this is a very general and pervasive idea that I think, or very general idea that I think is really an important one. And similar for those of you who know about reinforcement learning in details, or AI or machine learning, it's a little bit like auto diff. So we did a whole bunch of work developing all sorts of different methods that I don't have time to talk about. And so I just want to talk about one particular method we developed in order to exploit this reward machine structure. And it's called Q-learning for reward machines, or QRM. We have a more recent version called CRM that I'll talk to you about or mention at the end. But for the purposes of this talk, I'm going to tell you about QRM. So how does it work? So there we have our reward machine on the right, which does our patrolling task. And we're going to learn one policy. We're going to use Q learning, and we're going to learn one policy or Q value function per state in the reward machine. We're going to select actions using the policy of the current reward machine. But the secret sauce is the following. What we're going to do is that we're going to reuse experience to update the Q values functions on every transition via off-policy reinforcement learning. So even though we're actually physically in one particular state, or either in the environment or in our simulation, what we're actually going to do is a form of counterfactual reasoning to say that if we were somewhere else instead of where we are, what sort of a reward would we have gained as a consequence of performing that action? And we can do that by exploiting the structure of our reward machine, and we can also do it with linear temporal logic. So just to give you a very grounded example, we select an action. We update each Q function as if the reward machine were in that corresponding state. So in particular, if you see this little purple guy down here, if the purple guy goes to the D, if it's in U0, then nothing's going to happen and it's going to get a reward of 0. And for learning purposes, it's going to update its Q function at Q0 accordingly. However, even though it really is in that state of U0, it can counterfactually think about what would happen in U1, U2, and U3. And here I'm just demonstrating U3 for you because it's the most interesting. If it were to go to D and it was in U3, then the update would be that it would actually get a reward of 1. And then that discounted future return would be the return it gets when it progresses to the next state because it knows it progresses to U0. So those are our techniques or our baselines. And the important thing about the work is that the QRM and QRM with reward shaping, which I didn't talk about, preserve optimality guarantees of Q learning and reward shaping, converging to optimal policies in cases where we don't use function approximation, and that's guaranteed by the underlying Q learning. So just some quick experiments. We did experiments in discrete and continuous domains, and I just want to remind you that Q learning, QRM and QRM with reward shaping preserves optimality. The other techniques that we developed, we used hierarchical reinforcement learning, which does not preserve optimality, and which you'll see manifest in the experiments, but we generated a version that still exploits reward function structure, and it does a little bit better, as you'll see. So in the office world environment, where we're doing various different tasks in our office world that you've seen before, our technique, the red one, you will see in this graph on the x-axis, we have the number of training steps. On the y-axis, we have the normalized reward. And you'll see that our technique very quickly converges to the optimal solution. This is the normalized discounted reward. Whereas the hierarchical reinforcement learning techniques do worse. They actually are suboptimal and they're manifesting, they're converging to that suboptimal behavior. But the one with the reward that exploits reward machine structure does better. We see similar results in various Minecraft worlds that we experimented on. And an important thing to note here is that the Q learning, which is guaranteed to converge to the optimal policy, is just flatlining down here. You can see the blue line at the bottom. It will eventually get up to 1, but who knows when, after 10 to the 6th training steps, it was getting no reward. And that just speaks to how effective these techniques are and really helping us to learn better. In a function approximation domain using deep learning, we similarly are the red function, and we did exceedingly well and better than all the other techniques, the state-of-the-art techniques that we trained with at the time. So the last thing I wanted to talk to you about before wrapping up is just that in this talk, I may have suggested to you that that the reward machines are something that we specify, and that is indeed one way we can get them, but we can also generate them and we can also learn them. And I'm going to tell you about that just very quickly. So you might think from what I showed you that maybe I would write an automata structure directly, or maybe, as I alluded to at the beginning, I might use linear temporal logic and compile it into an automata structure, use linear temporal logic directly. I wanted to note that we can exploit Chomsky's hierarchy and this correspondence between finite state automata and regular languages to note that any regular language can be compiled into a corresponding finite state automata. So you can use any language that you want as long as there's a finite state automata representation and still exploit our techniques. And so what we advocate for, you could use the regular expressions, certain dialects of linear temporal logic or past linear temporal logic, regular expressions, linear dynamic logic, and all sorts of other things that you can translate into a DFA. And there are actually existing translators for a lot of these things because people use them in formal language theory. And then we can just write them as reward machines, which is very straightforward. We've got algorithms for doing that, and use all the different algorithms that already exist, like the ones that I've mentioned previously for reward machines, without having to write another tailored reward function structure manipulator. So that we can also generate reward machines using a symbolic planner, which we've done, a high-level planner that actually generates these structures for us. And we can also learn them in partially observable environments. And this is just a really simple example of a cookie domain where you have to press the button and then find the cookie and eat it, and your objective is to maximize cookies. It's very hard because it's partially observable, but what we've done is been able to learn a reward function structure that the agent can follow. And what's important about this too is that it's really quite human interpretable, I think, or can be made human interpretable from this structure that we've learned on the right. And using this type of work, we just, we are able to then solve problems that state of the art we're not able to solve, because partial observability is really hard in reinforcement learning. So just to recap, I was interested in how to advise, instruct, task, and impart knowledge to an AI that learns. There were lots of challenges of doing that, including reward specification and sample efficiency. My opinion is that the alphabet, compositional syntax, and semantics of formal languages can help RL agents learn what to remember and reason. Hopefully I've convinced you of that. And more generally, that formal language is a powerful and effective tool to advise, instruct, task, and impart knowledge to an AI. The big idea was in the talk was reward machines and exposing function structure through those reward machines. So lots of different papers that you can look at and code to play with if anybody is interested. And I think I'm probably right at time, so I'm going to stop sharing so that we can continue on. So thank you.